C# and AI Masterclass by Edgar Milvis Volume 8, Chapter 10. Turning our attention to Chapter 10, YAML Prompts and Serialization. Turning our attention to theoretical foundations. The fundamental challenge in constructing sophisticated AI agents is not merely invoking a large language model, LLM, with a static string of text. It is the orchestration of complex, stateful, and multi-step workflows where the structure of the prompt, the metadata governing the model's behavior, and the integration of external tools must be managed with the same rigor as database schemas or API contracts. Raw strings, while flexible, are brittle, they lack structure, are difficult to validate, and make versioning a nightmare. This is the problem that YAML prompts and serialization addresses within the Microsoft Semantic Kernel. To understand this concept, we must first anchor it in the architectural evolution of the semantic kernel. In Book 7, Chapter 9, we established the kernel function as the atomic unit of execution. We learned that a function is defined by its function view, a metadata structure containing parameters, return types, and descriptions. However, we largely constructed these functions using imperative C# code or simple string interpolation. As we transition to Book 8, where the focus shifts to agentic patterns, we realize that agents often need to compose these functions dynamically. They need to generate prompts based on context, inject tools, and manage conversation history. Hard-coding these structures in C# strings is inefficient and violates the principle of separation of concerns. Now, let's talk about the what YAML as a structured prompt definition language. YAML Ain't Markup Language, is a human-readable data serialization standard. In the context of semantic kernel, it is not merely a configuration file format, it is a domain-specific language, DSL, for defining the lifecycle of an AI function. When we use a YAML prompt, we are moving away from this code to a structured definition. Let's start by examining the core definition of this AI function. Notice how at line 1, we've given this function a descriptive name, summarize text. This name is crucial for discoverability and readability within our semantic kernel application. It allows developers to easily identify the purpose of this particular skill. From lines 2 to 6, we define the template, which is the actual prompt sent to the large language model, LLM. This template acts as an instruction set for the AI. We're telling the AI, you are a helpful assistant, line 3, to set its persona, and then instructing it to analyze the following text, and summarize it, lines 4 to 6. The $input placeholder at line 5 is where the text we want to summarize will be injected. This is a fundamental concept in prompt engineering, creating clear, concise instructions and using placeholders for dynamic content. Finally, line 7 provides a description of the function, which is invaluable for documentation and for tools like Semantic Kernel's Planner, allowing it to understand when to use this specific skill. Now, let's look at the parameters section from lines 8 to 12. This block defines the inputs that our summarized text function expects. At line 9, we declare a parameter named input, which directly corresponds to the $input placeholder we saw in the template. This establishes a clear contract for our function. Line 10 specifies its type as string, which is logical since we're expecting a block of text. Line 11 provides a description for this parameter, explaining its purpose, the text to summarize. This is excellent practice for maintainability and for anyone else who might use this skill. Lastly, at line 12, we set a default value to an empty string. This is a pragmatic choice. It means if the caller doesn't explicitly provide input, the function won't immediately fail with a missing parameter error. Instead, it will attempt to summarize an empty string, which the LLM would likely handle gracefully, perhaps by returning an empty or very short summary. Without a default value, the semantic kernel framework might throw an error if the parameter isn't supplied, stopping execution. This small detail enhances the robustness of our AI function. Let's discuss the anatomy of a YAML prompt. The configuration layer, config. This section defines the non-functional requirements of the prompt. It specifies the model to use, e.g., GPT-4o, the temperature, creativity versus determinism, and the maximum tokens. Crucially, this allows for model agnosticism. You can swap the underlying LLM provider, OpenAI, Azure OpenAI, Hugging Face, without changing the logic of the prompt itself. 2. The input schema. Input. Unlike raw strings where parameters are concatenated, YAML defines a strict schema. It declares variables, e.g., $user_name, $query, and enforces types. This enables static validation before the prompt is ever sent to the model, catching errors like missing required variables at load time rather than runtime. 3. The template logic. Template. This is the actual prompt text. However, it is treated as a template engine. It supports control flow, conditionals, loops, and variable substitution. This allows for dynamic prompt generation where the structure of the prompt changes based on the input data. Turning our attention to the why, serialization, versioning, and agentic scalability. Why introduce the complexity of YAML parsing and serialization when C# strings work? The answer lies in the lifecycle of agentic workflows. Now, let's talk about 1. Serialization and deserialization as a boundary. Serialization, C# object-YAML. This is the authoring phase. Developers, or even non-developers via UI tools, define the agent's behavior in YAML. The semantic kernel serializer converts this into an internal prompt template config object. Deserialization, YAML-executable kernel function. This is the runtime phase. The kernel reads the YAML, validates it against a schema, binds the C# parameters to the YAML variables, and compiles it into an I function that can be invoked. This separation allows us to store prompts in a Git repository, version control, a database, or a remote file system, decoupling the agent's logic from the application's binary code. Now, let's talk about 2. Versioning strategies. Semantic versioning of prompts. With YAML, we can tag versions. Classifier_v1.0.YAML, the baseline. Classifier_v1.1.YAML, added handling for sarcasm. Classifier_v2.0.YAML, switch to a reasoning model requiring different chain of thought instructions. Rollback capability. If version 2.0 hallucinates, the agentic system can dynamically load version 1.1 without recompiling the C# application. This is impossible with hard-coded strings. Turning our attention to 3. Modular prompt templates, composition. System_instructions.YAML defines the persona. Safety_filters.YAML defines content moderation rules. Task_specific.YAML defines the actual task. The deserialization process merges these contexts. This modularity is vital for agentic patterns like the planner, where the agent must dynamically select and compose subtasks defined in separate YAML files. Moving on to the how, the internal mechanics of YAML processing. To visualize the flow of data and control within the semantic kernel when processing a YAML prompt, consider the following pipeline. It moves from a static file to a dynamic execution context. This diagram illustrates the pipeline that transforms a static YAML prompt file into a dynamic execution context within the semantic kernel. Turning our attention to deep dive, the serialization process. Lexical analysis, the YAML parser reads the file. YAML significant whitespace is used to define hierarchy. This is parsed into a dictionary-like structure, JSON equivalent. 2. Mapping to prompt template config. The internal prompt template config class is a C# representation of the prompt. The deserializer maps YAML keys to C# properties. Here, we're defining a prompt template config class. Notice that this class serves as a conceptual representation of how we intend to structure and manage prompt templates within our application. It's crucial for encapsulating all the necessary metadata and configuration for a given prompt. Without such a structured approach, managing numerous prompts, their descriptions, input requirements, and execution parameters would quickly become unwieldy and error-prone. This class acts as a blueprint, ensuring consistency across all our prompt definitions, which is vital for maintainability and scalability in a complex AI engineering project. Think of it as a schema for our prompt templates. Schema validation. Before the object is fully realized, the kernel validates the input section. If a parameter is marked as required, true but lacks a description or type, the deserialization fails immediately. This prevents silent failures where a prompt is sent to a model with missing context. Turning our attention to deep dive, the execution context, handlebars versus liquid. Handlebars logic. Semantic kernel often uses handlebars syntax within the YAML template block. $variable, direct variable injection. Hashtag if condition, /if the conditional logic. Hashtag each list, /each iteration. Analogy, the restaurant kitchen ingredients, parameters. The YAML input section lists the ingredients, e.g., 2 cups of flour, user input. If you don't have the flour, you can't cook. Instructions, template. The template section is the step-by-step guide. It tells you when to mix, when to bake, and how to plate. Chef's notes, config. The config section specifies the oven temperature, and the cooking time, max tokens. The cook, kernel. The kernel is the cook who reads the recipe, gathers the ingredients, serialization/binding, and executes the steps, rendering the prompt. If you want to change the recipe, versioning, you don't rewrite the kitchen, you just swap the recipe card. If you want to cook for a different number of people, scaling, you adjust the input quantities without changing the instructions. Turning our attention to real-world analogy, the XML configuration versus YAML prompts. In legacy enterprise software, we used XML configuration files, web.config, to define connection strings and logging levels. We moved away from XML because it was verbose and hard to read. XML, old way, prompt name summarize /name text, /text prompt, too verbose, hard to nest. Raw strings, current pane, summarize this, plus input, no structure, hard to version. YAML, the solution, it provides the structure of XML with the readability of JSON, specifically tailored for natural language processing. Moving on to architectural implications for agentic patterns. Dynamic function creation. In Book 7, Chapter 9, we registered C# methods as functions. Now, we can register YAML files as functions. Here, we're looking at a conceptual snippet, illustrating how one might define and load a prompt configuration in a real-world semantic kernel application. Notice at line 2, we're reading a YAML file named summarize.yaml. This file would contain the prompt template, potentially with variables and configuration settings for the AI model. This approach promotes modularity and separation of concerns, allowing prompt engineers to manage prompts independently of the C# code. This is crucial for iterating on prompts quickly without recompiling the application. Imagine if every prompt change required a code deployment, it would significantly slow down development and experimentation, which is vital in AI engineering. Cross-platform compatibility. Because YAML is a standard text format, the same prompt definition used in a C# backend can be parsed by a Python frontend or a JavaScript client. This ensures that the prompt as code is consistent across the entire stack. 3. Testing and CI/CD. We can write unit tests specifically for our YAML prompts. We can assert that the prompt renders correctly given specific inputs. The output adheres to a specific schema, using JSON validation. The prompt does not exceed token limits, estimated via serialization length. Escaping special characters. YAML uses special characters like. When these appear in the prompt text, e.g., writing code examples in the prompt, they must be properly escaped or enclosed in quotes. The serializer handles this automatically, but it is a common source of error in manual editing. Multi-line templates, YAML's block scaler, is essential for preserving new lines in the prompt. Without it, the LLM might receive a flattened string, altering its behavior. Variable interpolation versus tool calls, a subtle but critical distinction. In YAML, $input is a variable interpolation. However, Semantic Kernel also supports syntax for function calling within prompts, e.g., fetch_web_data $URL. The deserializer must distinguish between data variables and function invocations, mapping them to the appropriate kernel function during execution. Moving on to summary. The shift to YAML prompts and serialization represents the industrialization of prompt engineering. It moves the definition of AI behavior from the realm of magic strings into the realm of structured, version-controlled, and composable software artifacts. By treating prompts as serializable objects, we enable the scalability required for complex agentic patterns, allowing systems to dynamically load, validate, and execute AI workflows with the same reliability we expect from traditional software components. Now, let's explore basic code example. Here is a simple, self-contained Hello World level code example demonstrating the YAML prompt format and serialization in Microsoft Semantic Kernel. Now, let's talk about the scenario. Imagine you are building a simple internal tool for a customer support team. The team frequently needs to summarize customer feedback emails. Instead of hard-coding a raw string prompt, we will define the prompt using a YAML file. This allows non-developers to tweak the prompt's tone and structure without touching the C# code, and it allows version control to track changes to the AI's behavior over time. Now, let's explore the code example. Here, we import the necessary namespaces. Notice Microsoft.Semantic Kernel, which is the core library for building AI applications with Semantic Kernel. Microsoft.Semantic Kernel .prompt templates, YAML is crucial for this example, as it allows us to define and load prompts using the YAML format, offering a structured and human-readable way to manage complex prompts. System.Component model is used for attributes like description that enhance discoverability and documentation of our plugin functions. System, text, JSON is a standard .NET library for JSON serialization/deserialization, often used implicitly or explicitly when working with data, though not directly used in this specific snippet. It's a common dependency in AI applications for handling model outputs or API responses. Finally, system, threading, tasks is fundamental for asynchronous operations, which are ubiquitous in I/O bound tasks like calling LLMs or external APIs, ensuring our application remains responsive. We define a simple C# class email plugin. This class serves as a native plugin, containing business logic that our AI application can invoke. The getLatestFeedback method is decorated with kernel function and description. The kernel function attribute is critical. It tells Semantic Kernel that this method is an AI callable function. Without it, Semantic Kernel wouldn't recognize this method as something it can orchestrate. The description attribute is equally important, especially for advanced scenarios like function calling with LLMs. It provides a human-readable explanation of what the function does, which the LLM can use to decide if and how to call this function. In a real-world application, this method would likely fetch data from a database, an external API, or a message queue, rather than returning a hard-coded string. This abstraction allows the AI to interact with external systems without needing to know their implementation details. We enter the program class and main method, the entry point of our console application. This is an async task method because most interactions with Semantic Kernel, especially those involving LLMs, are asynchronous. At line 19, we start initializing the kernel using kernel.createBuilder. This builder pattern is a common architectural choice for constructing complex objects like the kernel. It promotes a fluent API, allowing us to chain configuration methods. This approach separates the construction of the kernel from its representation, making the code cleaner and more maintainable. It also allows for flexible configuration, adding various services and plugins before the kernel is finally built. Here, we configure the AI model that our Semantic Kernel will use. Builder.add Azure OpenAI Chat Completion is used to integrate with Azure OpenAI Service. Notice the use of deployment name, endpoint, and API key. In a production environment, these would be sensitive credentials, typically loaded from environment variables or a secure configuration store, not hard-coded. For this example, we use dummy values. This configuration step is crucial because it connects our application to the underlying AI model, which performs the actual text generation and understanding. If this step were misconfigured, the application would fail to communicate with the LLM, leading to errors or non-functional AI capabilities. The builder build call at line 26 finalizes the kernel's construction, making it ready for use. This is where all the configured components are assembled into a functional kernel instance. At line 29, we register our email plugin with the kernel. Kernel.import plugin from object, new email plugin, email, is how Semantic Kernel discovers and makes our native C# functions available to the AI. The first argument is an instance of our plugin class, and the second argument, email, is the plugin's name. This name is important because it creates a namespace for the functions within that plugin. For example, if an LLM needs to call getLatestFeedback, it would refer to it as email.getLatestFeedback. This modular approach promotes code organization and prevents naming conflicts, especially as the number of plugins grows. Without this step, the kernel would not know about our getLatestFeedback function, and therefore, it couldn't be invoked either directly or via an LLM's function calling capabilities. This section defines the core of our prompt using a YAML-like string. This YAML prompt variable contains a structured definition of an AI task. Notice the name, summarize feedback, which gives a clear identifier to this prompt. The template block uses a multi-line string literal, which is excellent for embedding longer text without needing explicit new line characters. Inside the template, we're using a chat-based prompt structure with message role equals system and message role equals user. This is a best practice for interacting with modern chat models, as it provides clear role separation and context. The system message sets the persona and instructions for the AI, while the user message provides the specific task. The $feedback syntax is a Semantic Kernel placeholder, indicating that this value will be provided dynamically at runtime. This modularity is key to creating reusable and flexible prompts. Continuing our YAML prompt definition, we see the template_format, Semantic Kernel line. This explicitly tells Semantic Kernel how to interpret the template syntax, specifically recognizing the $variable placeholders. Below this, we define name, feedback and description, the raw feedback text to summarize, within the argument section. This is a crucial part of creating well-defined prompts. By specifying the expected arguments and their descriptions, we make our prompt more robust and self-documenting. It's akin to defining function parameters. The default, no feedback provided, provides a fallback value, preventing potential errors if the feedback argument is somehow not supplied. The execution_settings block defines parameters for the LLM call itself, such as max_tokens, 100 and temperature, 0.7. These settings directly influence the LLM's behavior. Max_tokens controls the length of the generated response, and temperature influences the creativity and randomness of the output. Higher temperature means more creative but potentially less coherent responses. These granular controls are vital for fine-tuning AI behavior for specific tasks. At line 52, we convert our YAML prompt string into a prompt template config object using prompt template config from YAML prompt. This step is essential because it parses the YAML string, validates its structure, and transforms it into an object that Semantic Kernel can understand and work with. It's a deserialization process, turning human-readable YAML into an internal data structure. This abstraction allows developers to define complex prompt logic in a clean, external format. YAML files are common in real projects, rather than embedding large strings directly in C# code. This separation of concerns improves maintainability and allows prompt engineers to iterate on prompts without requiring code changes. Following this, at line 56, kernel.create function from prompt config, takes the parsed configuration and creates a kernel function. This summarize function is now a callable entity within the kernel, encapsulating the prompt logic and its associated settings. It's the bridge between our YAML definition and the executable AI logic. Now we prepare the arguments for our summarize function. At line 62, we retrieve the latest feedback by invoking our previously registered native plugin function, kernel, plugins, email, getLatestFeedback, .invokeAsync string. Notice how we access the plugin by its registered name, email, and then the function by its name, getLatestFeedback. This demonstrates the power of Semantic Kernel's plugin architecture, allowing AI prompts to seamlessly integrate with custom C# logic. The result is awaited because invokeAsync returns a task. Then, at line 63, we create a kernel arguments object. This dictionary-like structure holds the values that will be passed to the prompt's placeholders. We map the retrieved feedback to the feedback argument, matching the $feedback placeholder defined in our YAML prompt. This explicit mapping ensures that the correct data is injected into the prompt before it's sent to the LLM. At line 69, we finally invoke the summarize function using await kernel.invokeAsync, summarize function, arguments. This is the moment where Semantic Kernel orchestrates the entire process. It takes the summarize function, which contains our YAML-defined prompt and execution settings, injects the arguments, our customer feedback, sends the complete prompt to the configured LLM, Azure OpenAI in this case, waits for the LLM's response, and then returns it. This single line abstracts away all the complexities of interacting with an LLM. The result variable will hold the summarized feedback generated by the AI. Finally, lines 72 to 73 simply print the output to the console. This demonstrates the end-to-end flow, from defining a structured prompt in YAML, integrating native C# functions, to executing the AI task and displaying the result. This modular and declarative approach is a hallmark of Semantic Kernel, promoting clarity and maintainability in AI application development. Using directives, we import the necessary Semantic Kernel namespaces. Microsoft.semantickernel.prompttemplates, YAML is specifically required to parse the YAML format into a prompt template config. 2. Email plugin class, we define a standard C# class decorated with kernel function. This makes the method callable by the kernel. GetLatestFeedback simulates retrieving data. In a real application, this would connect to a database or email server. It returns a simple string representing the customer's raw text. 3. Kernel initialization, we use kernel.createBuilder to set up the dependency injection container. Add Azure OpenAI chat completion is added. Note, the credentials provided are dummy values. To run this for real, you must replace them with valid Azure OpenAI or OpenAI credentials. Builder, build, assembles the kernel. 4. Plugin registration, kernel.import plugin from object, new email plugin, email, registers our C# class. This makes the function available to the AI model if we choose to use it as a tool, or to the developer to retrieve data for prompt arguments, as we do here. 5. The YAML prompt definition, we define YAML prompt using a C# raw string literal. Name identifies the function. Template, the actual prompt text sent to the LLM. Note the use of messaged tags, Semantic Kernel's XML-like syntax for chat roles, and the variable placeholder, $feedback. Template_format, specifies that this uses Semantic Kernel's standard format. Input_variables, defines the schema for inputs. Here, we define feedback, providing a description and a default value. This is crucial for validation and UI generation. Execution_settings, maps to LLM parameters like max_tokens and temperature. 6. Deserialization, prompt template config. From YAML. This is the critical serialization step. The static method from YAML parses the string, validates the schema against Semantic Kernel's expected structure, and returns a prompt template config object. This object holds the structured definition of the prompt. 7. Function creation, kernel.create function from prompt config, converts the configuration object into an executable kernel function. During this process, the kernel prepares the prompt template engine. 8. Argument preparation. We create a kernel arguments dictionary. We retrieve the feedback text by invoking the native function getLatestFeedback via the plugin collection. We assign this value to the key feedback, which matches the $feedback placeholder in the YAML template. 9. Invocation. Kernel.invokeAsync summarize function arguments triggers the execution. The kernel performs the following internal steps. 1. Renders the template by replacing $feedback with the actual text. 2. Sends the rendered prompt to the LLM. 3. Receives the response. The result is stored in the result variable. 10. Output. The summarized text is printed to the console. Moving on to visualizing the flow. This diagram illustrates how the YAML definition flows through the semantic kernel to produce a result. Let's discuss common pitfalls. 1. Mismatched variable placeholders incorrect, defining name, feedback but using $text in the prompt. Result, the template engine will fail to replace the placeholder, often sending the literal string $text to the LLM, or throwing a runtime exception depending on the strictness of the configuration. Fix. Ensure the name in input_variables matches the placeholder name in the template exactly, case sensitive. 2. YAML indentation errors result, YAML exception or invalid operation exception during deserialization. Fix. Use an IDE with YAML support, like VS Code with the Red Hat YAML extension, to validate indentation before running the code. 3. Missing template_format result, the prompt might not render correctly, or functions might not be invoked properly. Fix. Always explicitly set template_format, semantic kernel for standard semantic kernel prompts. 4. Forgetting to register native plugins result, the kernel throws an exception indicating the function or plugin was not found. Fix. Call kernel.importPlugin from object or import plugin from prompt directory before creating or invoking functions that depend on those plugins. By scanning this code you can go to the website with more details and with buying options. On leanpub.com you can find the discounted bundle with all the volumes. Thank you for your attention. This lesson is excerpted from Volume 8, Chapter 10 of the C# and AI Masterclass ebook series and from the volume, The Core of AI Engineering, Microsoft Semantic Kernel and Agentic Patterns. You can find all the details here, https://github.com/edgarmilvus/C# programming series. The ebook also includes 20 chapters with diagrams, advanced examples, and 5 exercises with solutions. Subscribe to the channel to watch more videos. I look forward to seeing you in the next lesson.